We know about elements now. These fundamental substances which can be combined together into other substances called compounds, giving us a wide array of different kinds of matter that we know and interact with. We also know about atoms, how they comprise these elements. These atoms bond together in order to form compounds. And when they do that, we have what's called a molecule. And this is kind of a recent addition to our formal knowledge because the technology and the insight necessary to be confident these molecules actually exist is fairly sophisticated. So it wasn't until the early 20th century that the last holdouts who said things like molecules and atoms didn't exist were forced to admit that they were wrong. Now, these two terms can be a little bit subtle in their distinction. So let's look at some examples here. If we have these subunits here where we have the same element bonded to itself, this would be an example of a molecule, since we have something fixed here. Whenever we have these little two things together, we know we have a molecule. But because there's only one substance, this is not a compound. Now, if we do have a second element, then we do have a compound. We still have a molecule. But we could also have different elements associating with each other in some sort of infinite lattice that extends in all directions. So because there's not a fixed subunit, usually we do not call this a molecule. But being made up of multiple elements, we would go ahead and call it a compound. Well, how do elements actually combine into molecules? We could divide this into two possible situations. The first is where we have covalent bonds. These generally involve a nonmetal interacting with a nonmetal. Recall that nonmetals, they want to have electrons. So they will often form negative ions since they pick up electrons. Well, one way that they can get these electrons they desire is that they can associate with each other. And so here we have hydrogen, which has one electron, and we have another hydrogen, which also has an electron. These two hydrogens can combine together in order to give us hydrogen gas. And this is true for many of the nonmetals, that they form these diatomic gases. Another way that we can have these substances combined together is through ionic bonds. This usually involves a metal and a nonmetal. And so the metals like to give away their electrons. The nonmetals like to receive electrons. And so in this case, the electrons are going to shift to the nonmetal. And when they do that, the nonmetal is going to pick up some negative charge. And the metal, which lost its electron, is going to have a positive charge. But when you have a positive charge and a negative charge, they're attracted to each other. So we form these ionic substances. These different types of bonding lead to different types of compound. So in the first case, where we have that covalent bonding, we could have what's called a molecular compound, which involves one or more nonmetals. Nonmetals, we're going to include hydrogen, which sometimes it acts as a metal, sometimes it acts as a nonmetal. And these are all covalently bonded together to make our molecular subunit. So something like methane is CH4. And so this formula here tells us that we have one carbon and 4 hydrogens associated with it. And this is called a molecular formula whenever you have a formula that gives you the exact quantities of the atoms involved. We could also have an ionic compound where we form those ionic bonds. Now remember that those ionic bonds, those involve transferring electrons between different elements. So we're going to have some things with negative charge and some things with positive charge. And what's different about this case is that if you have a negative charge, then any positive charge would love to associate with it. And so we get these networks involving lots of different charges all bonding to each other. Now, the way that we would write the formula for something like what we have here, where we have sodium and chlorine combining together, is we would write NaCl. Now, this is different because we don't have just one chlorine bonded to each sodium, and we don't have just one sodium bonded to each chlorine. So this doesn't tell you how many things are attached to how many other things, like the molecular formula does. But what it does tell you is the ratio. So if we were to calculate out the total number of chlorines and the total number of sodiums in this NaCl, we would find that the numbers were basically the same. And so we have a 1-to-1 ratio between chlorines and sodiums. And so that's what this formula tells us. It tells us the ratio of atoms. And if we had twice as many chlorines, then this would be NaCl2 instead of NaCl. Now, when we have a formula that just tells us the quantities, that formula is called an empirical formula. With a virtually infinite variety of possible compounds that we could form, as scientists, we're going to need a good specific way to tell other scientists which compound it was we did our experiments with and which compound it is that we are submitting a sample of. We're going to split our strategy for naming these substances into naming molecular compounds, where we have those fixed subunits, in which case we can just name the subunit, and having ionic compounds, where we have those ratios. And so then we have to come up with a way of communicating what the ratio of ions is. Now, if we have a molecular compound, this is actually the more straightforward case. So we just need to name all of the different atoms in our compound, and we need to say how many of them there are. So we're going to start with the most metal-like of the elements. Recall that the periodic table, in the bottom left, there are metals, and in the upper right, there are nonmetals. So as you go further down and to the left, you have more metal-like elements. And so those will be the ones that get the name first, and then we will proceed to name the other elements. Now, when you get to the very last element, you're going to chop off the last couple of syllables and replace them with "ide." So, for example, if you had hydrogen and oxygen, hydrogen is more metal-like. It's more left in the periodic table than oxygen. So it will be named first. But instead of saying hydrogen, oxygen, in order to make it so that it sounds like we're actually, coming to the end instead of just listing a whole bunch of different things, we will say oxide. So that would become hydrogen oxide. Now, of course, we could have more hydrogens or more oxygens. And so we're going to need to indicate the actual number of atoms, and we do that using a Greek prefix. So just a reminder of those Greek prefixes. So mono is 1, di is 2, etc. So if you had 2 hydrogens and 1 oxygen, that would be dihydrogen monoxide. Now, these last vowels, they can get chopped off. So like monoxide, or tetroxide, pentoxide, we can dispense with that ah sound if there's a vowel that we're combining it with. But if we have a consonant we're combining it with, then we might say tetrahydrogen or pentahydrogen. In that case, we would keep the ah sound. And when we have just a single atom, we can put the mono here, but if we omit it, then that implies that there was just one of them. And so this mono is frequently omitted in our nomenclature. Let's say that we want to name the compound which has 3 oxygens and 2 nitrogens. First thing we're going to need to do is consult our periodic table. The reason we need to consult our periodic table is because we don't know whether we need to start by naming the oxygens or we need to start by naming the nitrogens. We look at our periodic table, and whatever is further down and left is the one that gets named first. So we look here, oxygen is to the right of nitrogen. So since nitrogen is further left, we will name that first. So we'll have nitrogen and then oxygen. Now since oxygen is the last element which is named, we chop off its syllables at the end and replace them with "ide." So we now have nitrogen oxide. Now the last piece of information we need to build in is the fact that there are 3 oxygens, 2 nitrogens. So we use our Greek prefixes. The Greek prefix that means 2 is di, and we have dinitrogen. And the prefix which means 3 is tri. So we have trioxide. We have named that molecular compound. As another example, let's say that we want to name CO2. So now we're starting with a formula. The formula is already in order. So we can just write down that we have carbon and we have oxygen. And again, we'll change the ending to "ide since it was the last element that was named. And again, the prefix which means 2 is di. Now if we want, we can write mono here to signify that we only have one of these carbons, but mono is generally optional. If we omit to write it, then you will know by the fact that there's no prefix there that there's only one of the carbons. The other major class of compounds that we're going to want to name is our ionic compounds. Now, our molecular compounds came in fundamental units, these molecules, and so we could name just the components of the molecule, and that would convey the information of what the compound was. Our ionic compounds do not come in those fundamental subunits, but what they do have is they have fixed ratios of the number of cations, the positively charged ions, to the number of anions, the negatively charged ions. So in order to convey what ionic compound we have, we will name the cation, we will name the anion, then we will, just like before, chop off the ending of the anion, the thing that we've named last, and give it a suffix. And as before, that will tend to be "ide." And then we also specify the charge in the cation. And this provides enough information that someone whom we're communicating this information to would be able to figure out how many cations and how many anions are present in our ratio. And we do this using Roman numerals on the cation charge. So let's say we have this formula. We have 2 sodiums for every 1 oxygen. So we are going to name the cation first. That's going to always be the metal. The metals are the ones that give away their electrons and become positively charged. So we name sodium, and we name oxygen, chopping off the ending and adding "ide. And then we specify the charge on the cation. This sodium is an alkali metal. It's in that first column of the periodic table, which means it's going to form a +1 ion. So we write a 1 here to name the charge of the cation. You might be wondering how it is that specifying the charge in the cation provides the information of how many cations there are to how many anions. Well, this information can be inferred by applying the rule that the compounds must have an overall neutral charge. We take the charge from all the cations and multiply it by their number, and the charge from the anions and multiply it by their number. It has to add up to 0. This is true of bulk substances in general. There are so many atoms and molecules in just a flask of something that if those individual molecules and or atoms had charges on them, and they were all the same charge, that would be more than enough to cause an immediate vehement explosion of the substance. So if you ever have something standing in front of you and it's not exploding, you can be pretty confident that its overall charge is neutral. So let's take an ionic compound, titanium oxide here. We have our metal and our nonmetal, so it makes us confident that it's an ionic compound. Let's try to figure out the name for this compound. Well, if we look up titanium, which is a transition metal, so we can't use our main group ionization rules, we find that it could be either +3 or +4 in its ionic charge. So which one is it going to be? Well, we know that oxygen should be -2 because it's a main group element and it's 2 to the left of the noble gases, which means it would like to pick up 2 extra electrons. So in order for this to be the compound, we find that only +3 works. And let's just confirm that. So if we have +3 for titanium, and we have our 2 titaniums, that adds up to +6. And then we have our 3 oxygens, each with -2, adds up to -6. So +6 plus -6 gives us a total of 0. So we're happy with that. So we will name it the cation first, the metal, titanium. Then we will name it with the anion, and we'll chop off its ending and replace it with "ide," so titanium oxide. And then to specify that we have the version of titanium oxide with the +3 cation instead of the +4 cation, that's why we need this Roman numeral here. And now if we give this name to someone and they know about these charge rules, then they will know that the only possibility for this compound is titanium 2 oxygen 3. But if we had a compound where there was no ambiguity, and so only one of these charges was possible, then in that case we could go ahead and omit the Roman numeral. And that's fairly common to do. So if we had something like calcium chloride, calcium only forms +2 ions, chlorine only forms -1 ions. So even if we don't write in the cation charge explicitly, the only possible formula for this ionic compound is calcium with 2 chlorines to compensate for the +2 charge in the calcium. Well, let's say that someone was giving us a sample of aluminum sulfide. What is the ratio of the aluminum atoms to the sulfur atoms? Well, to interpret this, first of all, let's consider the sulfur from the sulfide. So that's a main group element over on the right side of the periodic table, and it's 2 groups left of the noble gases. So that means it would like to pick up 2 electrons to reach that noble gas configuration. So it will have a -2 ion associated with it. Aluminum is a little bit further left. It's also a main group element, and so it is 3 groups to the right of those gases. If we start on the far end and we loop back over to the other side of the periodic table on the far left. And so since it would like to lose 3 electrons to reach the noble gas configuration, it will have a +3 charge. Now we can go ahead and apply the rule of wanting to maintain a neutral charge in order to figure out what the exact composition is. So what we've written down so far, we know that aluminum, our cation, is +3 charge. We don't know how many aluminums there are. We know our sulfur is -2 charge, and we don't know how many sulfurs there are. And we know when we add them together, this all has to add up to 0. All right, well, let's go ahead and move this over to the right side of the equation. So we have -2y. If we add 2y to both sides of our equation, that will get rid of it on the left side. So in that case, we get +3 times x is equal to +2 times y. Well, what could we set x and y equal to make this a true equation? Well, it's pretty easy. If we multiply this 3 by 2, and we multiply this 2 by 3, 2 times 3 definitely equals 3 times 2. So that will solve our equation. That must mean that we have 2 of our aluminums and 3 of our oxygens. So this is the formula for that substance, Al2O3. We also have what are called polyatomic ions. These are just like our regular ions made out of single atoms, but they are comprised instead of multiple atoms. And these atoms together, they have an overall charge, which makes them ionic. You might think of these kind of like molecules. Depending on who you ask, molecules are supposed to not have any charge on them, but some people go ahead and consider these molecules. And so when we want to name compounds involving these polyatomic ions, we actually do it pretty much the same way that we do it when we have single atoms that we're dealing with. So if we have something like MgC2O4, we would recognize this C2O4 as one of our ions up here. So that's oxalate. You can see it has a -2 charge associated with it. And just like with our other ionic compounds, we name the cation first, our metal. So we write magnesium. We name the anion second. In this case, we don't need to change the suffix. It already has a suffix built in this chart here. Note that it's not always "-ide". Frequently, our oxygen compounds have 8 in them. And then, just as usual, we give the charge on the cation, which is +2. Many of our polyatomic ions consist of some element plus a varying number of oxygen atoms. So there's a specific way of naming these compounds in order to distinguish them from each other. First of all, if there's only one form in which there is the element plus oxygen to form some ion like this, then we name the element and then we add an 8 suffix to it. So here we have chromium, and chromium has oxygen attached to it, so we will go with our 8 name nomenclature, and so we call it chromate. And there's only one possibility here. But what if we have multiple possibilities? In that case, we are going to distinguish the different versions by reference to how many oxygens are present. So this is our default choice. We will always have this 8 here. But if we have one that has less oxygen, we will also have an ite. So we'll have an 8 and an ite. Now if we have a third element with even less, then we'll call it hypo to distinguish. We have even less than before. If we have a fourth element with an extra, then we will use this per in order to name it. And so this one you might have to look up. You might have to know which the 8 version is. But once you know what the 8 version is, then you can know any of these other versions. So for example, we have varying polyatomic ions involving chlorine and oxygen. So this is our starter here. ClO3- is named chlorate. And if we've decided to call that chlorate, then that must mean with 4 oxygens is perchlorate. With an oxygen less than 3, we'll have chlorite. And with 2 oxygens less than that 3, we'll have hypochlorite. There's also a special naming convention if we have ionic compounds which contain hydrogen as one of the ions. These are actually acids, and so we name them as hydro, then the root of whatever the anion is, ic, and acid. So for instance, say that we have HF. This is our nonmetal, the F, and hydrogen is acting as our metal. So that makes it an ionic compound. So this F is fluorine. So we would chop off the last syllable, just write fluor. So we have hydrofluoric acid. That's how we name HF. Now again, we can have those varying quantities of oxygens come in. So if we have a polyatomic ion here acting as our cation, and we have a few versions of it with varying quantities of oxygen, then we will start with this as our default case. So we will name that Ich form. And then if we have something that has one less oxygen, then that will become the Us form. If we have one that has two less, that will become the hypo blank Us form. And if we have one that has an extra oxygen compared to this case, then it will be the per Ich form. Let's consider those varying chlorine polyatomic ions again. So we would have hydrochloric, refers to the ClO3- case. And we have an extra oxygen, is perchloric acid. One less oxygen is hydrochlorous acid. And then finally, we have just one oxygen, it becomes hypochlorous acid. The final special case we'll consider is when we have what's called a hydrate. So this is where we have an ionic compound, and it's loosely associated with some water molecules. They aren't actually bonded in the same sense that the atoms are ionically bonded to each other, but they're still part of the overall formula of the substance. So the way we name these is we go ahead and name the ionic compound, that portion of it, just the way we usually do. And then we just throw in a Greek prefix to indicate how many water molecules are, in general, associated with each formula unit of the ionic compound. And we use a dot kind of in the center to show that we have these water molecules loosely attached, but they aren't actually bonded as part of the formula. So if we add copper sulfate, and we add 5 waters, then we write this dot and say that there are 5 waters to go along with each Cu and each sulfate. Say you were given this formula here. We have cobalt, 2 chlorines, we have our dot, and we have 6 water molecules. The way that we're going to name this is we're going to name the ionic portion. And once we've named that compound, then we can throw on the hydrate portion of it. So this is cobalt, this is chlorine, which becomes chloride. And the charges here, I suppose since chlorine is a halogen, it's always -1. And since there are 2 of those, cobalt better be +2 in order to make sure we have a neutral compound. So we have our cobalt 2 chloride, and we have 6 waters, so in a Greek notation that is hexahydrate. I have a picture here. So here is the cobalt chloride, and here is the cobalt chloride hexahydrate. And the presence of the waters shifts the energy levels of the electrons in this ionic compound, giving a different hue when you look at it. And if you wanted to, you could interconvert back and forth between these all day. You could heat your hydrate over here to drive off the water, and it would turn blue. And then you could add some more water back to it in order to hydrate it, and it would turn pink over here. So that's what we mean by saying these aren't chemically bonded. We can basically transition between these as a physical change rather than a chemical change.